This is Lecture 17, The Coast Range and Continental Margin. The lecture material primarily comes from the Oregon Geology by Oren Orr. Moderately high mountains, terraces, rocky headlands, sandy beaches, and offshore shelf and slope all contribute to the province's varied landscape. Because of the marine influence, the province has the warmest average winter temperature, the coolest average summer temperatures, and the greatest precipitation of all the provinces of Oregon. The highest elevation is Mary's Peak at 4,097 feet. Only two rivers, the Columbia and Umpqua, cut entirely across the province. Along the shores, abrupt headlands are punctuated by bays, estuaries, pocket beaches, dunes, and spits. By Miocene time, marine sedimentation was confined to areas close to the present-day shoreline. Note the deposition of the Naya-Deep marine silts and the Astoria shelf sands within the Newport embayment. The Yaquina deltaic sediments underlay both the Nye silts and the Astoria sands. Note the Columbia River basalts were flowing down the then existing Columbia River and would eventually invade the Newport embayment, forming the headland features that bracket today's Moolock and Beverly Beach. This is the Astoria Formation at Beverly Beach. Sedimentation began in the early Miocene and continued into Middle Miocene. These are thick to thin-bedded, very fine to medium-grade micaceous and carbonaceous arkosic marine sandstones and sandy siltstones. They are commonly fossiliferous with calcareous ledges and concretions. Both dacitic tuff beds and basaltic sandstones are found interbedded in the formation. The sandstones and siltstones show bioturbation. The fractures in the lower mudstone are from shrink swell caused by repeated wetting and drying. The large holes were started by eroded calcareous nodules up to 10 centimeters in diameter found in the formation. Their removal and subsequent erosion creates the bathtub effect you see in the photograph. One of the joys of geology is finding fossils. Moolock Beach's Astoria Formation is a world-renowned site loaded with fossil invertebrates and the occasional vertebrates. Some people go to the beach to find agates, but some of us are on the lookout for neat fossils. The fossils were a part of the ecology that lived on the Miocene continental shelf. The upper left is a Siliconradi, a bivalve found in coastal tidal environment during the Miocene. Upper middle is Andara devincta, another Miocene bivalve. It is an indicator fossil for the Miocene. Middle upper right, Patinopecten is a large scallop up to about 10 centimeters in size. Very common. Middle lower left, Chione cancellata is a shell with a cross-hatch pattern similar to steamer clams found today. Middle lower right, Macoma arcata, has a thin flat shell, often having a hole drilled by snails, which then ate the clam. Lower upper left, Chlorostoma pacifica, a gastropod or snail with a short rounded design and a well-defined whorl. Lower upper right, Prepidula praerupta, an extinct androgynous claw-like snail which moved in colonies linked together. Lower right, Ficus modesta, a snail with a well-rounded shell with a fig-like shape and delicately lined whorl. And lastly, lower left, Dentalium schnecki, a snail sometimes known as a tusk shell. Look for something that looks like the end of a drinking straw in the formation. This photograph is of the ginkgo flow of the Frenchman Springs member of the Wanapum Formation of the Columbia River Basalt Group at Yaquina Head. They are subaerial and subaqueous flows with extrusive breccias, tuff breccias, and pillow lavas composed of glassy tholeiitic basalts with sparse labradorite phenocryst. Also note the narrow sea stacks on the right of the image. This Columbia River basalt group flow exhibits essentially uniform chemical properties through the bulk of individual flows, suggesting rapid placement. Ho and Cashman 97 characterized the 500-kilometer long ginkgo flow of the Columbia River basalt group. They determined that it formed roughly in a week based on the measured melting temperatures along the flow from the origin to the most distant part of the flow and combined with hydraulic considerations. The ginkgo basalt was examined over its 500-kilometer flow path from a ginkgo flow feeder dike near Calotes, Washington, to the flow terminus in the Pacific Ocean at Uquinna Head, Oregon. The basalt had an upper melting temperature of 1095 plus or minus 5 degrees centigrade and a lower temperature to 1085 plus or minus 5 degrees centigrade. This indicates that the maximum temperature drop along the ginkgo flow was only 20 degrees centigrade. The lava must have spread quickly to achieve this uniformity. Analysis indicated that the flow must remain laminar, as turbulent flow would cool much more quickly. This could be accomplished by sheet flow, which can travel at velocities of 1 to 8 meters per second without turbulence and minimal cooling, suggesting that the ginkgo flow occurred in less than a week. The cooling hydraulics analysis are supported by independent indicator. If longer periods were required, external water from temporarily dammed rivers would have intruded, resulting in both more dramatic cooling rates and increased volumes of pillow lava, which were not found. Ho's analysis is consistent with the analysis by Rydell et al. 1994, who proposed a maximum Pomona flow in placement duration of several months based on the time required for rivers to be reestablished in their canyons following a basalt flow interruption. The youngest structures in the study area are the Pleistocene terraces found at the top of most of the Astoria Formation sea cliffs. The terraces contain unconsolidated thick to thin bedded, plantar, and cross-bedded fine to medium grain marine and non-marine sands with lenses of rounded pebbles and gravels. Dark paleosols are found within the lower portion of the terraces. The upper surfaces are iron-stained dune sands. Carbon-14 dating of fossil wood found within the terrace deposits are greater than 35,000 years before present. The terraces along the top of the coastline from Uquinna Head to Otter Crest are strath terraces. Strath terraces are terraces that are etched into bedrock as compared to alluvial terraces that are cut into stream alluvium. These terraces were initially wave-cut platforms that were cut into the bedrock by continuous wave action, by biological activity of clams and sea urchins boring into the rock, and by the evaporation of seawater and precipitation of salt in small fractures within the rock itself. The Oregon coastal province does not stop at the beach, but extends out onto the continental shelf that dips gently seaward to 600 feet and to the lower slopes that descend to the abyssal seafloor depths of 9,000 feet. The offshore topography is mantled by sand and muds, producing flat areas that are folded and broken by banks, ridges, basins, channels, and canyons. 20 miles off Uquinna Bay, the Stonewall Bank lies in water less than 120 feet deep. Beneath the Heceta Bank, a basalt ridge buried in the accretionary wedge marks the western edge of the Eocene Silesia oceanic terrain. West-northwest trending left lateral strike-slip shear faults run from off the coast across the deformation front, the accretionary ridge, and onto the abyssal plain. 9 20 to 70 mile long faults lie between Cape Blanco to the central Washington coast. These shear faults mark the boundaries of elongated blocks dated from 650,000 to 300,000 years before present that are rotating clockwise due to the northwestward push of the subsiding Juan de Fuca plate. The most notable of these are the Wacoma, the Daisy Bank, and the Alvin Canyon Valley faults, where fault pop-ups are occurring at the intersection of the faults with the deformation front. The accretionary ridge is made up of imbricated sheets of deformed tertiary sediments and basaltic rock, lie at the foundation of the shoreline shelf slope off of Oregon and Washington. Tied to subduction, the earthquake cycle for Oregon proposes that during an interseismic period of low activity lasting hundreds of years, strain accumulating at the interface between the Juan de Fuca plate and the North American plate causes coastal uplift. When the strain is released, an earthquake, rapid subsidence of the coastal region, and a tsunami take place simultaneously. Chris Goldfinger, an OSU researcher, offers evidence that indicates that different portions of the subduction zone act independently of one another. He assessed the 10,000-year history of the subduction events and found that southern Oregon and northern California have experienced megaquakes greater than 8.0 magnitude that occur every 250 years. Central Oregon experiences one every 500 years, and northern Oregon and Washington every 500 years. The last major quake occurred around 1700 AD in the vicinity of northern Oregon and Washington. Chile experienced a 9.5 magnitude event in 1960, with the Chilean coastal areas experiencing as much as 6 feet of coast seismic release. This map illustrates the apparent rate of uplift along the Pacific coast expressed in millimeters per year. The north-south discrepancy in numbers are a function of interseismic strain accumulating along the subduction boundary between the two plates. The north or south areas are active while the Newport area is static. It leads one to assume that when the large earthquake occurs, it will happen at the subduction zone opposite Cape Blanco. A large earthquake at the Cascadia subduction zone, triggering a displacement of the continental plate, will cause a tsunami that will impact the Oregon coast. The wave will travel at speeds up to 600 miles per hour. The wave will appear as a low, broad wave in the open ocean, and as it approaches the shallower coastline, it may pile up to 100 feet in height. A succession of destructive waves from a single earthquake may last for several hours. Waves, prevailing wind, tide, climate, currents, and sea levels are all working to modify the coastal morphology. While the sandy beaches are being rapidly reduced, the level terraces and protruding bluffs are also being steadily consumed. Erosive processes are tied to cycles of turbulent wintertime ocean that contrast with some moderate summer conditions. The Oregon coastline has been characterized as one of the highest wave energy environments in the world. Tillamook Spit was the site of the city of Bay Ocean, the queen of Oregon resorts, and was an early planned community on the coast with streets, houses, a natatorium, hotel, grocery, and a bowling alley that were erected in the 19-teens. Erosion caused by storm waves cut 3 gaps into the peninsula, dashing hopes for the planned community envisioned. The last resident left in 1952. The major geologic hazard along the Oregon coast and within Lincoln County are mass movements or landslides. 3 types of mass movements are common in the coastal range and on the Oregon coast: slumps, debris flow, and rockfall. Slumps occur when large blocks of bedrock move downslope like the Johnson Creek landslide shown in the photograph. Debris flows are shallow water activated mass movements that occur in steeper terrain. They are generally associated with the soil horizon and move downslope as a muddy slurry. Rockfall occur when large chunks of rock break off of their parent rock and plummet to the ground. Landslides in the Newport area have caused the destruction of homes and property values. As a result, the city of Newport has installed restrictions concerning building on bluffs overlooking the ocean. The backyards of these Newport homes lie in an active landslide zone. The city plans to adopt updated maps of areas prone to slides and erosion, a change that will affect building codes. Angry property owners are fighting the change, saying their land values will sink. Well, duh. One of the largest Oregon coal mines was the Beaver Hill Mine. Oregon coal mines supplied much of San Francisco's coal supply starting in the mid-1850s. Oregon coal mines prospered up into the mid-1880s when coal prices plummeted and they ran into employee trouble. Since most Oregon coal mines had been bought by outsiders by that time, the mines began to fold. Oregon coal mines once numbered over 70. The final blow to coal prices came when ships' ballast was being comprised of coal. When the ships unloaded in San Francisco, they also sold the ballast, thus driving coal prices down and helping to bring about the demise of Oregon coal mines. A block of a gas hydrate, methane clathrate, recovered from seafloor sediments off the Oregon coast. A gas hydrate occurs when methane gas escapes from sediments on deep ocean floors, lock into a lattice of water where temperatures are cold enough to freeze or solidify the mixture. Hydrate Ridge, about 60 miles off of Newport, is especially rich in hydrocarbons. Legislation has banned oil and gas drilling within 3 miles of the coast. The Devil's Punchbowl on Cape Foulweather is a collapsed sea cave. You can see large blocks that have fallen from the cave ceiling to the floor of the Punchbowl. Occasionally, you will see tourists in the Punchbowl at low tide, a very dangerous place to be as the tide rises. Large paleo dune fields lie along Highway 101 between Newport and Geohazards. These dunes were in place during the last glacial stand when sea levels were lower. Since that time, Uplift have placed the dunes at their current elevation. South of Cape Perpetua to Coos Bay, a large influx of alluvial sediments and prevailing winds have created large sand dune fields in excess of 150 feet in height. Numerous freshwater lakes were created by the damming of small streams by the dunes. Two of the most beautiful peaks in the Coast Range are Saddle Mountain and Mary's Peak. East of Seaside, Oregon, the twin peaks of Saddle Mountain are composed of Columbia River basalts. The highest mountain in the Coast Range is Mary's Peak. It is composed of Silesia basalt, a part of the Silesia terrane, marine plate, that was thrusted upward due to compression. I want to thank you for a great semester. So much of this semester was spent looking at the past. The future we can only predict from the evidence we have discovered. The world is a beautiful place, and only our curiosity can make it meaningful.